Hey, hello. Amazing, some of you are still awake. Impressed. Okay, so the first announcement. Some of you, possibly not the people in this room, but maybe your friends, did not get to run on hardware over the hackathon. So 2 notes on that. If you didn't finish in time and you just are really curious what will happen with your program, please just send an email to Matt or support@IonQ.com for further access to the computers. We're totally happy to make that happen for y'all if you didn't get a chance. And then secondly, if you are interested in a more involved project, we do have a research program that provides grants to run a quantum hardware to folks affiliated with the university. So through your professor, or if you're a grad student yourself, or as an undergrad, if you're doing a research project, you are more than welcome to apply. You can just Google that, go to our website, or again, just email Matt@IonQ.com or support, and we're happy to tell you more about the program. We'd love to have you be a part of it. The other thing I'll note is we don't have an office in Boston, unfortunately, maybe one day, but we do have headquarters just outside Washington, D.C., on the campus of the University of Maryland, where we were spun out of. And we're opening new offices in Seattle and Toronto, Canada this year. So if you live near any of those places, or you occasionally visit those places, we love giving tours to high school and college groups, so please reach out. We'd love to have you come by as part of a program, or just with an interested and enthusiastic group of quantum folks. And with that, I will turn it over to some members of our applications team and part of the judges for the hackathon today to talk about some recent research we've been doing.
Cool. Yeah, hey everyone, I'm Jason. I'm an applications engineer or scientist at IonQ. I guess I'm going to talk a little bit about some of the projects that we've got going on, looking at applications, how we could actually implement these, or state-of-the-art trapped ion quantum computers that we have, and study and scale to solve real-world problems that are interesting both to academia and to industry partners. So one of the major focuses at IonQ is quantum chemistry. So here we have some results that we recently published, one of the largest VQE simulations of lithium oxide chemical. We think it's a record for end-to-end training of VQE for a chemically accurate simulation on a molecule of this size. So you can see in this figure here that the energies, after some slight error mitigation, these 2 points run on the ARIA quantum computer. There's no laser. Anyway, 2 red points here. After doing some slight error mitigation, basically line up essentially perfect agreement with the exact eigenenergies. And you can see here some other similar VQE simulations done in the community. Anyway, these 2 points. So you can see here, this is the exact simulation, right? And we have noisy quantum computers, so the raw data measurements that you come out are these points here. But they're basically following this curve exactly if you shift by an amount that's related to the expected error from the quantum simulation. So once you do that shift, you get basically chemically accurate energies. And so, these variational simulators to find the ground state energies of chemicals, they're very involved. They have very long circuits. So simulating chemicals of any size is actually quite difficult. So being able to do it on 12 qubits already with this generation of computers, it's a pretty huge accomplishment. And as this scales up to 20, 30 qubits, if you could get similar chemical accuracy type simulations, it will be state-of-the-art, beating classical computers, we expect. Other big focus area at IonQ is quantum machine learning. Huge number of different areas of machine learning have applications. We are particularly interested in programming our quantum computers to do computer vision problems, problems that our industry partners are particularly interested in. And so we have a number of these really exciting machine learning problems that we're tackling. So one thing here is like image classification. It's sort of the first thing you start out with when doing machine learning. It's the first thing we start out with as a proof of concept for quantum machine learning. And so using, replacing the machine learning model with a quantum circuit, we were able to do end-to-end training on our ARIA quantum computers on models with 4 and 8 qubits, basically. And we're also able to do inference on trained models on models with up to 16 qubits. And this is basically large enough that we can start projecting how the advantage is going to play out as we scale up to larger systems and run these simulations on more numbers of qubits. But this is sort of a toy implementation of a problem that someone who does machine learning at industrial scale might actually be interested in. And so we're also working on more complicated problems, particularly 2D object detection and 3D point cloud analysis, which are problems that are more difficult. There's very complicated classical machine learning approaches to these problems that suffer from certain drawbacks. And so we have a variety of unique approaches to tackling these problems that hopefully could give some quantum advantage on these very hard problems. So this is something we're actively working on that way.
Hi, everyone. My name is Dai Wei. I'm also application scientist at IonQ. Next slide. OK. I'm going to talk about some project that I want to emphasize are at IonQ and are led by interns or undergrads that work with us through the past summer intern, and maybe throughout the year. So if this project sounds interesting to you, yeah, feel free to reach out to us. You may be continuing working on this, or totally feel free to explore in similar direction, similar to this. So if you have if you worked in this, of course, you all worked on the hackathon, and one of the merging problem you probably have encountered is that we have a limited quantum resource, right? In particular, qubits, number of gates. So now you have a classical problem. How would you encode your problem onto, how would you let your quantum solution see the problem, see the configuration? You have to put the problem, like definition, the image you want to classify onto your quantum system, right? So you basically have to encode that into quantum circuit. But we only have a limited resource. So how to compress those information, how to efficiently encode them onto quantum circuit is a very hard problem, and a lot of people are studying them. In the past year, we had interns study this Q-pixel encoding, which is a particular encoding scheme that lands between what's mostly popular sparse encoding and dense encoding. These days, the sparse encoding and dense encoding, they're kind of a two extreme of efficiency versus, memory efficiency cost, operational cost, versus operational cost. And this somewhere lands between. And above there, we also study the, We also study the quantum autoencoder. So if you have a classical encoder, you can use a neural network to train and cut off the network, isolate the thinnest section at it, and that will be your hidden vector, right? And at that hidden vector, your information got encoded into something very, very efficient. Of course, you have to reconstruct later if you want to use it, and that may give you some error, but efficiency is very high, could be very high. So we have some quantum version of it. And intuition is basically if you first put your information onto quantum circuits, you can also use similar variation operation to squeeze your quantum information onto last number of qubits. And you can just dump the rest of the qubits or reinitialize them, right? And with this, you can store information, compress the information in your quantum circuit. You have some loss, but you can still have reasonable reconstruction. And the other stuff we also did with our interns for the past year is a lot related to this graph neural network. So the idea of graph neural network is basically unlike normal neural network, you have connection between layers, between neurons in each layer. In this framework, your information basically pass between the nodes of on your graph, right? Like illustrated here. And why would you do this? Because when you do normal neural network, a lot of time you do this convolution operation. What does convolution operation do? It's basically enable you to impose some symmetry. It's basically say these 4 pixels are next to each other, and you don't have any other information on the graph. You would say this 4 pixels in your framework should be totally identical to the other. You shouldn't have more other assumption to the other 4 pixels with similar configuration, right? So whatever information extraction you do with this 4 pixels, you will do it the same here. And the graph is basically a more abstracted description of such symmetry. So if you capture such information and you use this, it may give you more advantage in a lot of application. And in many times when people use it, it's just because your data is naturally represented by a graph, say social network, right? And use this. And on one example, we used this for circuit optimization. In this study, I think it's by Google, it's published, they use reinforcement learning to compress circuit or optimize circuit, right? Many times people just do circuit optimization by hand, and a lot of that is just experience, what gates should you combine, and so why can't we teach a machine learning agent to do that, right? And then the question comes, how should we give the concept or give the image of the circuit to the machine learning agent? In some case, you might just put it into your image and feed it to the machine learning agent. But we think use graph to represent the circuit, because circuit naturally is just the relationship between all the operations, right? That may be a better way to do this. So we have been studying this, and we have getting some very interesting results. Another example is you use 3D point cloud. When you study 3D point cloud, the 3D point cloud aren't like images, right? They're not really, you are given like index of this is like which points in my graph. But what is the index of the points in the array doesn't really matter. It only matters what their like coordinates and where they are with respect to the other points. So to handle that symmetry, if you do it with standard neural network technique, quantum or classical, would impose a lot of overhead. So we think using quantum graph neural network, you can encode such symmetry in your data into this graph neural network or the structure that you aggregate information and gain a lot of benefit. So that's another very cool thing that we have been doing. Again, that's the end of my part. Just want to say this work, our very cool work, are led by our interns and undergrads hire. So if you want to join us, this will be the cool stuff you may be working on. Yeah.
Okay. Hi, everybody. I'm Shayoni. I'm also a quantum application scientist with Daiwei and Jason at IonQ. You have heard about all the cool stuff regarding image recognition, classification, all the stuff we are doing with computer vision. And this slide is about generative learning, and you did a bit of that during hackathon. And this work is mostly based on generating financial data and prediction in risk aggregation tasks using financial market data. So this is another work that was done by IonQ last year. And what you see here is this, to me, it's very uninteresting, right? Financial data. But anyways, here you have some variables, and what you want to do is basically capture joint distributions of these multiple variables, right? And that can be a hard task, like sampling from distributions and, in general, approximating probability distributions. So here, what they did is, and Daiwei is one of the authors in this paper, you load this data in a way on a quantum circuit, and then you train your quantum circuit, this is a variational quantum circuit, to learn this distribution. And what you do essentially is you make measurements on a quantum computer, and this is your quantum circuit, you make these measurements, and this gives you some sort of a histogram, and you train your quantum circuit using your generated histogram and the target histogram, and you optimize the parameters in your quantum circuit, right? So this is your generator in your generative model, and they were able to reproduce these multivariable distributions as well as predict some extreme tail events, right? So this is one task where they were successfully able to predict certain events. And some other cool stuff that you can do with generative models, and it's a question to all of you, is here. Like, can you do cool image recognition problems, object detection, something that both Jason and Daiwei talked about? What else can you do? Can you generate different molecular structures? Or let's say even beyond generative models, if you look at in general quantum applications, you want to estimate ground state energies, then you have these optimization problems, right? So those are also very complicated problems, and yet very cool ones, and you have a lot of places where these can be useful. And these are, again, some chemistry applications, modeling different molecules, right? So these are all of these different application areas we work in general. And if you are interested in working with us as interns or in full-time positions, please do come and talk to us. And Corey will be discussing a bit more about what positions we have, right?
Yeah, internships and entry-level roles. So I'll get to specific ones we have open at the end. But first I'm going to talk about why it's fun and why you should join us. Reason number one, we're a small company. I think what's nice about working as someone entry-level or as an intern at a small company is that at IonQ, we all end up doing a lot of different things, mostly because we don't have enough people to each do a specific thing. So it makes a lot of sense. So as someone who is starting out, it's a really incredible opportunity to gain a lot of experience in different disciplines within your role. And there's a ton of flexibility in what you can work on. And the other thing that's nice is there's not really enough people to micromanage. So even interns and entry-level employees will have a lot of autonomy and ownership over what they work on, which is a pretty special opportunity when you're just starting out. I do want to point out, though, the reason our internship program is so small is because everyone has an assigned mentor. And I actually did an internship with IonQ. And I think the nice thing about having an assigned mentor who has signed up to have an intern and who is voluntarily doing this is that they are very available to help you with the hard parts of your project. And when you are doing real work, that is really helpful. The other thing is we're very supportive. It's a very supportive culture. So my mentor, when I interned, actually made me this T-shirt when I finished the project. I actually finished it a couple months ago. It carried into my full-time role, which is also special in intern projects because a lot of times that shit just gets thrown out. And so it's really cool to be able to actually work on a thing that ends up getting used and that you can finish. But it's called we call it the SDK. It's a internal, basically, interface for our physicists to run experiments on our quantum computers. And I should have worn that T-shirt. That would have been hilarious, but it does exist. And just generally, IonQ is a great place to learn because people are really willing to explain what they're doing and go into depth if you want. Everyone is incredibly patient because none of us really understand what anyone else does, so you have to be patient, which makes a really cool environment. The last thing is we've got big goals. So we're getting less small. Now we're like 200 people, which I think is like a mid-sized company, which is insane. But we're still trying to do a lot of things. So we still have that startup vibe. We're trying to manufacture production-grade quantum computers. That's happening in Seattle. We just opened that office. It's the first office to do that for realsies, which is kind of fun. We're going to continue to build R&D systems with longer and longer chains. And throughout all of that, though, we're still a relatively small, focused team. So like I was saying before, even though you can come in without a lot of experience, you will end up getting to do something useful because, again, we don't have time to not do something useful, which is like a unique opportunity as someone with not a lot of experience. Daiwei already talked about some past intern projects, but these are some outside of applications. We have people working in optomechanics. We have people working in computer automation. That's what I work in. It's really fun. Environmental control software. Basically, a ton of different types of engineering and more physics-based opportunities. We also can work out a semester-long co-op if that is a vibe. We don't have like a formal program, but you can definitely reach out. And then for full-time roles, we have electrical engineering, experimental physics, so they work on like actually making the quantum computers. Different kinds of mechanical engineering, quantum applications and algorithms, as well as software. And a lot of these are entry level. They don't require any experience, so come join us. And internship applications technically are closed, but you can reach us at Matt's email. Or if you filled out like our little iPad survey, we're gonna look through those resumes after the hackathon. And also reach out if you're unsure what role you fit in, and we can see if we can work something out. That is all I have. Come work for us. That's all.